This is a series of 4 videos that addresses some topics in the theory of linear programming and is subdivided into 4 videos. The first video, part 1, we're going to first introduce some notations that will be used throughout these videos. And also we're going to review linear programming, specifically the simplex algorithm and simplex tableau and the formula associated with simplex tableau. And the second video, part 2, will address degeneracy, which is an issue for the simplex algorithm that may cause the algorithm to cycle. So the first method, we're going to state and prove a blend rule. And the second method is we're going to address epsilon perturbation of the right-hand side, which leads to non-degenerate simplex tableau. And that will lead to the well-known lexicographic methods for simplex algorithm. And the third video, using those results, part 3, we're going to address in detail phase 1 of the simplex algorithm and all the possible outcomes of phase 1. And finally, the fourth video, we're going to state and prove the important fundamental theorem of linear inequalities and its corollary, the well-known Farkas lemma and all its variants. And finally, we're going to address the geometry of polyhedral set, where we're going to state and prove the decompositions of theorem of polyhedral set. That is, a polyhedral set is the sum of a polytope and a polyhedral cone. I'm Dr. Mohammed HAMAMI, and please, if you have any comments, send me emails at mhamami1781@gmail.com. So now let's introduce the notations. So if you have a matrix A, it's an M by N matrix. So A, the element are denoted by A of ij, so I represent the row, J represent the column. Then I'm going to denote by A of dot I. This is just the ith column of A. So it's just A of 1i, A of 2i, etc., A of mi. And similarly, A of j dot is the jth column of A, which is A of j1, A of j2, etc., till A of jn. Okay. Now, if we have a beta, an ordered set of indices, let's say beta 1, beta 2, etc., beta k, then A of dot beta is just a sum matrix of A, where the column are this column, A of dot beta 1, A of dot beta 2, etc., A of beta k dot, A of dot beta k. Similarly, if I have a set of indices, gamma 1, gamma 2, etc., gamma L, then the notation A of gamma dot is just the matrix whose rows are defined by these indices. That is, here goes A of gamma 1 dot, A of gamma 2 dot, etc., till A of gamma L dot. And finally, if I have A of gamma beta, that is just a sum matrix of A, where we pick these columns and we pick these rows. All right. So this is the notation that we will be using often. Now let's discuss elementary operations on a matrix A that are used in the simplex algorithm and also in the Gaussian eliminations. So elementary of a row, elementary operations. The first one is we replace row I by a multiple of that row, alpha times row I. In other words, we take a row of I and multiply it by this number alpha. That's one elementary operation. The other one is we take a row I and replace it by row I minus alpha row j. In other words, we take a row I and then we subtract from it a multiple of another row. So these are called elementary operations that are used in the simplex pivot and also in the Gaussian eliminations. Now I go remind of a fact from linear algebra. So this is linear algebra. Let's say we have a square matrix. A. And then I form a tableau like this, A, and then attach to it the identity. Okay, I remind you the identity, it's just a square matrix whose column is 1, 0, 0, 0, 0, 1, 0, etc. and then 0 here, and then all the way down to 1, 0, and 0. So it's a 0 everywhere except in the diagonal I have ones. So if I have a square matrix A and attached to it the identity matrix, and then I do elementary operations, okay, I do the elementary operation, and I was able to transform it to this. The identity on this side and some matrix B here. Okay, just by doing this two type of operation I was able to make this side the identity and this side B. Then from linear algebra, B, from here, B is equal to A inverse. Okay, that's a known fact in linear algebra, because every row operation, this one operation, is like multiplying by a non-singular matrix on this side. Same thing with this one. So overall, then you add all those multiplication of matrices, that gives you a matrix B such that BA will be equal to the identity, and therefore B is A minus 1. So let's define what a linear program is. So we want to minimize linear form C transpose X subject to a system of linear equation A dot X equal to B and X is non-negative. So here X is an n-dimensional vector. These are usually referred to as the decision variables. C is also in Rn, and they are usually referred to as a unit cost. So this C transpose X is some type of cost that we want to minimize. A is an M by N matrix, and B is an M vector. Okay, so that's what we are trying to do. We want to find the X that satisfies this equation and also make this expression the smallest possible. So if you want to program this, then you're going to set an input your matrix A, your right-hand side B, and then I'm going to add another equation representing the objective function. So I'm going to write Z equal to C transpose X, or C transpose X minus Z equal to 0. So in here, I'm going to add another equation. Here, C transpose, and here we'll have 0, 0, minus 1, and 0. This column corresponds to this Z vector. So I represent this linear program by a system of equations. Now let's assume that, so what is a simplex tableau? So let's assume that we transform this into a tableau like this. A bar, B bar, C bar, and then our Z variables, and here minus theta bar. Okay, let's assume that through elementary operations on the rows, we were able to transform this system of equation to this system of equation. First, I mean, the two systems, since we're doing just row elementary operation, the two systems are equivalent. Solving this system of equation or this system of equation is the same. But this form right here has three properties. One is that B bar is greater or equal to 0. Every entry in the right-hand side is greater or equal to 0. The second property is that the identity matrix is in A bar. The column of the identity matrix, remember the 1, 0, 0, 0, 1, 0, 0, and so forth, they are somewhere in here in A bar, all of them. Not in the same order, but they are somewhere in here. So those will be called basic columns in here, and the other column will be called non-basic columns. And the third property is that C bar I is equal to 0 for I basic. Okay, so if I have, so under the identity matrix, the column of the identity matrix, the coefficient here is 0. So if I have this three property, then this is called the simplex tableau. Okay, once we have a simplex tableau, once we have something like this, then we could go ahead and optimize this using the simplex iterations. So let's write down some formula with this first. Let me remind you of some formula with this. Since we started with this matrix and we were able to put the identity matrix here, right? Then A bar, remember the fact that we stated earlier from linear algebra, it's just equal to A dot beta minus 1 times A, where beta is just beta 1, beta 2, beta m. This is the list of indices where the identity matrix is. So beta 1 will be the index where 1, 0, 0, etc. 0 is. All right? And beta 2 will be the index where 0, 1, 0, 0 is, and so forth. Then from the fact from linear algebra, A bar is just A dot beta minus 1A. And the same thing, B bar is just A dot beta minus 1 B. And C bar C bar transpose is, was obtained from C by canceling the element under the identity matrix. So this will be just C transpose minus C beta transpose times A bar. Okay, so somewhere here I have 1, 0, 0. Then I multiply by the C beta to cancel that term. Then you see here the C bar beta is equal to 0. Okay. Then so these are our formulas. So we have this 1, 2, and 3. Okay, and I remind you that when you're doing the revised simplex method or the regular simplex method, you know what this inverse is. So you could always compute A bar, B bar, and C bar. And also theta bar. I didn't talk about theta bar. Theta bar, that's 4. Theta bar, it's just C beta transpose B bar. So we have a simplex tableau here, and we defined what the beta is. It's just the list of the indices for the basic column. So this is called the basic feasible index. In short, we will be referring to it as a BFI. And let's define the complement of this, beta bar. It's just 1, 2, and minus beta 1, etc., beta m. So this is the non-basic columns. Okay. All right. So now I'm going to define a new solution. So which I call X bar. And here I define it by X bar of beta bar equal to 0. In other words, for the column that are not basic, I set my variable equal to 0. So what's left is just the identity matrix, and I'm going to set those variables equal to beta bar. So X bar of beta equal to B bar. Okay. This solution here clearly satisfies this set of equation, and therefore satisfies this set of equation because the two are equivalent. And of course it's greater or equal to 0 because this is 0 and B bar is greater or equal to 0. So this is a solution to my system of equation. This is called the basic feasible solution. In short, we call it BFS. Okay, so every simplex tableau has a basic feasible solution associated with this. Now let's calculate what C bar transpose at X bar. That's equal to just to C bar transpose beta X of beta plus C bar transpose of beta bar times X bar of beta bar. And that's equal to C bar beta. This is 0 because C bar I is equal to 0 for I basic. So this term is 0. And then this term here, X beta bar is 0. This term is 0. So this is plus 0. So this is equal to 0. So when we plug in X for X by X bar, this term is 0. So what's left is Z equal to theta bar. Okay, and remember what Z is. Z was set up to be C transpose times X bar. So in a simplex tableau, the theta bar that's here, it's the value of my objective function when we replace X by this value x bar. And the objective then of the simplex is to make this theta bar the smallest possible. So this is a review of the simplex tableau, the basic feasible solution, and the basic feasible index. So now let's move to the next section when we discuss degeneracy.